Hello, my name is Aaron Mazzeo, and I am going to be presenting information about Lab 3 on colliding electrons. This work builds on that of Jonathan Singer and Rahman Pejman. And we're going to simulate a couple scenarios. One where we have a couple of electrons that are colliding with each other, and then another when we have 3 electrons colliding with each other. Now, since we're dealing with electrons and their interactions, we're going to think about the forces that are involved, and it's a repulsive force if they have the same charge. As we discussed in class previously, we have potential energy associated with a pair of electrons, and this Ke is called the Coulomb constant, and we have the charges and we have a distance. But then we take the negative of the gradient to figure out what the force is, and then this is the Coulomb constant times K1 or Q1 Q2 over R squared, and then it has some direction. Now epsilon, the Coulomb constant is often represented in terms of the permittivity of free space or vacuum, and so that is 8.854 times 10 to the minus 12 farads per meter. So when we start this problem, we might want to create a function that's able to apply this force. And as we've said in class, sometimes it gets a little bit murky in terms of what we do with keeping track of the negative sign in this term, okay, depending on how we define distances. So let's go to MATLAB, if it will let me, okay, and we're going to create a function that's going to give us a force for a Coulomb interaction between two electrons, and it's going to be dictated by the distance between them and the charges that are entered into the system. So for this, we'll say we have force arising from Coulomb potential. That's fine, and I guess we can call it QE1, QE2, whatever. Sorry. Okay, like that. In our case, since they're both electrons, they're going to be the same. And we can define our permittivity of vacuum. So this is permittivity of free space. And we can define the force. And here we'll have a negative sign. And this is going to be the magnitude of the force. So we won't output a vector here, just a scalar. Like that. And be sure to remember the semicolon, because if you don't, which I've done, then it will print it out every time it calls the function, and that can slow down your simulation in addition to being annoying. Alright, I think that looks pretty good. Oh, I called them QE. So let's make sure we do that. Yeah, QE1, QE2. Okay, good. So now we get to the opportunity to model the colliding electrons. And so for this, we'll put kind of some of the standard commands at the beginning. Okay, and we're going to have a code that will be easily modified for us to be able to handle more than 2 electrons. So right now we're going to say n equals 2 for the number of particles. Okay, but we are going to implement our non-object oriented architecture to be able to handle using more particles. So for that, we can look back at what we covered in class in how, instead of doing object orientation, what we have is non-object orientation. So we represent the positions okay, of all of the particles in our system with column vectors, where each row represents a parameter or property of the particle. So uh, this would be the x position, and that would be the x1 would be the the x component of the first particle, all right, and y1 would be the y component of the first particle, okay. And so you see these column vectors go here. So if we only have two particles, we're going to have 2 by 1 vectors, all right, and our velocities will similarly be given by two column vectors, u and v. This is the x velocity, this is the y velocity, and u1 and u2 are going to correspond to particle 1 and particle 2. And we're doing this problem in 2 dimensions, so we're not going to have z and we're not going to have w. So we go back here, and we will also input the mass of an electron, which is very small. Okay, and we will define the field of view, and this is not the space over which we can operate, but this is just the field of view that we're going to be using as we run and just watch the simulation progress. Okay, and it's going to be in units of meters, so we're going to be looking at plus or minus the cell value, and that gives us essentially a 1 centimeter square. And that's kind of a large area when you think about the size and the speed at which things are happening in this simulation with two electrons. Of course, this is not well, I guess it is kind of particle physics, but it's not particle physics in the sense that when we slam these electrons each other, we're not going to be looking at um, uh, what flies off, okay? And we're saying that the electrons they stay complete, and they're just particles and mass and charge. So when we define our initial positions for these two particles, we're going to say the x's and the y's, and I'm going to make it a column vector. So what that means, this is a row vector, but when you use this little apostrophe symbol, that does the transpose on it. So that will spit it out as a column vector. Okay. And that's going to be in units of meters, and they're both going to be on the horizontal axis. So both components are going to be y, or both components are going to be, both y components are going to be 0. Okay. Good. Okay. We're also going to specify initial velocities. And in this case, we're going to give particle 1 a nice little kick of, 10 to the 5th meters per second in speed in the x direction. So that's going to be the x component. So 100,000 meters per second. That's pretty fast. Okay, and our time steps are going to be very small, or the time step is going to be very small. So we're just going to use 0.1 picoseconds. So a picosecond is 10 to the minus 12 seconds. Nanosecond is 10 to the minus 9. Microsecond is 10 to the minus 6. Millisecond is 10 to the minus 3. So this is 0.1 picosecond in time step. And we're going to look at running over a total time of 100 nanoseconds. Now, why did I put this around here? Well, one thing that you might notice when you start doing math in the MATLAB, as great as it is at handling many decimal places, sometimes little rounding errors occur. So if I do 1 e to the minus 7, right, divided by 1 e to the minus 3, what you'll see here is, yeah, it's like 10 to the 6, but it's kind of, right? So let me emphasize this just a little bit. If you look over here, okay, I didn't clear all my parameters. Let me clear all my parameters. Whoops. I don't have, okay, so if I come, or I do it again, and I come up here, what you'll see, this is the answer in the workspace. It looks like it might be good. It says, 10 to the 6, but then if I really look at it, it's 9.9 repeating times 10 to the 5th. All right, that's almost 10 to the 6, but I want to end right on my 100 nanosecond time. So if I do round of this answer, okay, then I get a nice number. Then it's actually 10 to the 6. Okay, so it's just something to be aware of, that even in MATLAB, which does a great job of handling these small numbers, we do want to make sure that we have, at least at the beginning, the whole values, or the whole integer that we're interested in having, right? So we're also going to be plotting at a frequency that is much less than the one tenth of a picosecond. So we're going to plot once per nanosecond. Okay, just like that. Okay. Now we can use some tricks that Professor Singer has outlined in his approach to this type of problem in handling these unique base pair interactions. So what's going to happen is we're going to look at how particle 1 and particle 2 interact with each other. And there's going to be a force between them, and then there'll be an equal and opposite force on particle 2 from particle 1, okay, and or vice versa, right? So we say fx12, this would be fx21 here, and they're equal and opposite from Newton's third law. And we keep doing this, so we have interaction between particle 1 and 3. And you see here, right, what are we building? In the first row, okay, of this, we're adding up all the contributions of the other particles on particle 1. Okay, so it's how does particle 2 act on it? How does particle 3 on it? And we're just doing superposition, and this is in the x direction. Similarly, right, we'll have all the interactions on particle 2, okay? Right, so particle 1 will be acting on it, particle 3 will be acting on it, right? And we're keeping track of these interactions in the summation of these column vectors. Well, we do this for fx and fy, and if we had a third dimension, fz, but to implement it in MATLAB, what we can do is create a matrix of particle pairs that makes sure that we don't do any double counting. So that is possible by defining, so pairs is not a function, but it's a matrix that we create, and it's got ones above the main diagonal, okay, using this upper triangular function, the trio, okay, and ones of the number of particles that we have in our system. Okay, so we're going to go ahead and create that in MATLAB so that we can use it later when we look at this is for Leonard Jones, but when we look at our our Coulomb interactions. So we're going to create a pairs matrix. I guess we only create it once, and that is going to allow us to have the ability to go through with these unique pairs. So as you've seen in the past, I like to kind of either plot or record the initial conditions and keep track of them. So in this case, we're not doing the same type of counting with container arrays. What we're going to be looking at here is how things evolve, and we're going to be plotting it. We're going to be plotting it, every nanosecond. So now is not a bad time to go ahead and do kind of the initial lay of the land, or plot the initial lay of the land. So this is going to be like our initial plot, and we're going to create a new figure, and we're going to just scatter plot particle 1's position. Whoa. Okay, that means blue circle. We're going to do a hold on, and we're going to scatter plot also particle 2's position. And we're going to do this red circle. Okay? And when we do that, that allows us to uh, see them in different colors, which is helpful as they will interact with each other. Now, I like to use title, if you hadn't noticed, or the title of my plots to kind of help me keep track of what's going on. It's excellent for troubleshooting. Okay, and so what we're going to do is we're going to have the title give us the velocity of particle 1. And initially, right, it's been defined here as 100,000 meters per second, so it's pretty fast, okay? And I'm taking, so US VS, right, that's going to give me the x and the y components of velocity, and vec norm will calculate the magnitude for us automatically. So that's kind of nice, and num to string allows it to be spit out into a into the title or into a label. Okay, so that's those are some useful commands. I've now lost track of my parentheses. Okay, yeah, and then that's going to be in meters per second. And then I'm also just going to spit out the x position of the first particle. Okay, so we'll keep track of this, and you know, as we run the simulation, we're going to see this evolve. And here I'll say that's in units of meters. Okay, and I like this ability to create multiple lines in the how do you say it, title, so that I can put multiple things that we're interested in. So for example, and then I'm copy and pasting here, right? So I've got now speed 2 for the second particle, and we'll keep track of the x position of that second particle as well. Okay, and the last thing we'll plot, the third line, is we'll plot the evolving time. And at least in the first, all right, or the initial step, that's not very interesting. I just put 0 here. Okay, but it tells me that's going to be there. And then the x label, like so, and the y label, like so, and those are in units of meters. I like to make the font size a little bit bigger, and then we'll do a hold off, and we're going to plot our field of view. This is going to be the negative, whoops, x, positive x, so that's defining the horizontal width, and this will be the negative y and the positive y. Yeah, it's not the most, you know, it doesn't say x equals this, but it just, that's how MATLAB handles it. And so that the lines that we plot look and have the appropriate angles without distortion, we can use axis square, so that will, since this is, you know, the same width and height, when we do a square, that means that we will not distort anything. We're going to draw now, and we're going to pause for 2 seconds before we go into the next set of commands. I like this because I like to be able to see, okay, did it set up everything correctly initially? Okay, so maybe you've seen some errors, but now we'll see if MATLAB finds errors with what I've typed. Okay, so here's one. All right, so the title, something is wrong here in line 30. Okay, so what did I do? It says vec norm untitled title dot dot usually it's more helpful with what's going on. Oh, US. Okay. Okay, so it doesn't like, okay, so it's saying that that's what it is. So see, look, excess, no, US. All right, so that's a mistake. Thank you, MATLAB. That could be a big bug later on. All right, let's see. What else? Oh, I didn't fix it the second time. Or no, it's that should be okay. Let's see. So now there's, what's it saying? Okay. Dimensions of array being concatenated are not consistent. Okay, so that it doesn't like this. US VS1. Let me just see. What is US? I'm sorry. VS 0. Yeah, okay. So what does it has an issue with that? Oh, it's probably this vector. Okay, so it's probably hold on, it might be a global thing. So the speed, This is where you fast forward through the video until I figure out what I've done. Yeah, I think I need a comma. That's why. Let's see if that works. Still, no. What is it saying? Not consistent. This is embarrassing. Okay, that goes with that. That goes with that. Okay. Okay, that's num to string. That's why. I think that's it. Yep, that was it. Okay, and so what we see is a plot of our two particles, okay, just like that. And actually, I see that I made a boo-boo. All right, I actually want the blue particle to be on the left of the right one, okay, because the x velocity is positive. So, see, even doing that little plot, I find that that should be a minus right there. Okay, so let's plot it one more time, and we should be good to go. Okay, and actually, I just found another boo-boo. This should be 1. All right. Lots to keep track of. Okay, so now we're ready to do some integration. We're ready to do some Verlet integration. So for this, I'm going to run. We're going to run through our iterations. Now, t often is not, I mean, you often think of time as like, the actual time. In this case, because we're going to reserve I and j for handling the base pairs for the particles, we'll say that t is an integer. And when you saw that, we were talking about the fx and the fy, right, as being the summation of all these base pair interactions. It's important to make sure that we initialize them to have zeros. Now this is not that interesting a vector, it just is a 2-column vector, but it is important that we make them both 0, because if we look at what we have here, okay, we're going to be populating it with these base pair interactions. And this is a conservative field, and it's only dependent on position. The forces are only dependent on position. So we have to make sure that before we calculate the force with all these base pair interactions in this electrostatic field, that we have set them to 0. So when we go through the iteration again, we're going to reset it to 0. Okay, and then, or we go to the next time step. Okay, and this is using the code that Professor Singer demonstrated to be able to populate those force vectors, those column vectors, appropriately with the base pair interactions. Okay, so this is going to apply to unique particle pairs, right? So we don't want to double count, and that's why we use that upper triangular matrix in the process. Okay, this is going to give us the distance between the x distance and the y distance between our selected base pair of particles, like this. So that's a y distance. And this will give us then essentially the vector norm, right, that we just talked about, or the magnitude, okay, of that distance. Initially, everything is just aligned horizontal, or the two particles are aligned horizontally. So the dx is going to be something. It's going to be actually, we know it's going to be 3 millimeters, and the dy is going to be 0. Okay, and then this is a column vector. We're using the transpose there for these differences, and we're going to divide by the magnitude. Okay, and so this is going to be a unit vector for the distance between particles. Okay, and then we're going to use the Coulomb function that we defined, okay, to calculate the force between ith and jth particle. Okay. I guess maybe I should have gone to Verlet for a second. So if you go back to, or when I say Verlet, we're using Verlet, right? But and this is from session 2. All right, there are 4 steps. So the first step in this velocity Verlet integration is to calculate a half velocity. But in order to calculate a half velocity, so we have our velocity at current time, right? Which we said the initial velocity of that one particle was screaming at 100,000 meters per second. So we have that initial velocity, and then we need 1/2. All right, so this is where half velocity comes in, right? So normally it's just at, right? But here we have 1/2 a times delta t. All right, so we need to figure out what that acceleration is, and in order to figure that acceleration, we need to use the electrostatic potential, or the negative gradient of the electrostatic potential, and divide by the mass. So once we have that force and we divide by mass, then we can calculate out the acceleration. So we have this is a scalar, right? That gives us a scalar, and we know the direction of that base pair interactive force, but we need to now update our fx and our fy matrices, as we see here. Okay. So this is going to be the x component of force on particle I. This is going to be the y component on particle I, and f times r2, like we have here. Okay, and if we go back to the slide, what we see is that we're populating these unique base pair interactions. Whoops, where did the mouse go? That's disturbing. Okay, well, it's it's this slide. Okay, okay, good. The mouse is back. We have our fx, right? That we're populating with these base pair interactions, and now we're essentially looking at these positive terms, like so the fx12, fx13, fx23, fx24, right? And that's what we've just done. But there are also these negative ones, these negative fx12, right, or f21, which would be the negative of fx12. Minus fx13, minus fx23, minus fx24, etc. So, well, they're not actually the 2, 4, and 2, 3 in this case because, well, we only have 2 electrons. So for this, for the interactions or how particle J gets affected, what we do is we write out that we have fx of J now. And that is going to be based on, okay, what were the other interactions before we got to this base pair interaction? And we're going to use the negative. We're going to do, sorry, so we're going to do subtraction of what we have here. So this is the x component of force on particle J, okay? And this is going to be the y component of force on particle J. Okay, which is equal and opposite by Newton's third law to what we just had. Okay. So finally, we've calculated the forces, which is nice. Okay, and we can do 3 n's. Oof, that's kind of cathartic. All right, because we're still in our integration loop, but we had 2 4's and a conditional statement. And we can now update the velocity after figuring out the force and the acceleration. Well, actually, we need to divide by the mass in order to do that still. So we're going to do a update on the half velocity. Okay, and this is going to be us equals us plus fx, all right, that we've been calculating. Okay, and this is going to be a half velocity in x direction. Okay, and we'll have the fy y direction, like that. Okay, and the next step in relay is to update the position. Oops. Okay, so let's see. Is this it? Yeah. So we got to update the position. All right. Based on using the half velocity that we've just calculated. So we have our current position, and we want to figure out where our next position is using the half velocity. So in MATLAB, what we do is we have an update on the position, and we have here our xs being updated. Okay, so where are we? Plus now this velocity that we just calculated. Okay, and so this is an update position in x direction. And ys, we're going to have an update, okay, in the y direction. Okay. Okay, so now that we updated position, what do we have to do? We have an opportunity to calculate out a new acceleration, okay, from the electrostatic potential using our new position. Okay, and why do we do that? Well, we want to then calculate a new, so we're going to use that to calculate a new velocity in the next step. All right, so if we're going to calculate acceleration, that means we need to update and calculate a new force at that new updated position. So we updated position. So if we updated position, we need to go ahead and get rid of the forces that we have in our fx and fy, okay, column vectors. So we're going to zero them again, and then we're going to run, I just copied and pasted, we're going to run the same exact commands to figure out the forces, and then once we updated the forces, we're going to run the same exact update on the half velocity, okay, and then we should be done with our our uh, our our calculations for this relay integration. But we would like to draw if it's been 1 nanosecond, if it's been a second, if it's been 1 nanosecond, we do want to draw. So now we're going to draw. So we're going to do some plotting. And if we have a remainder of 0, okay, with respect to our reporting interval, okay, we will go ahead and we'll do our scattering, our scatter plot. So we come back up here, we can also copy and paste. That makes our lives a little bit easier. Okay, so we come over here for that initial plot, and we're just going to copy all that stuff except for the pause, and we don't need to make a new figure. Okay, we want to update that figure, so we can just copy and paste that in. Okay, and one thing that's useful, all right, is I can select this, I can hit Control I, or I can right click. Whoops, I think I just had troubles. So I right click. Oh, that didn't do so well, so I'm just going to do it the shortcut way. Control I will then put it nicely indented. Okay, and after I do that drawing, I can go ahead and, well, end that conditional and then end the loop. All right, and let's see what happens. So probably some errors. Actually, no. All right, we're error-free this time. All right, so pause for 2 seconds, and now we see that blue particle on the left nicely runs in to that red particle. Ooh, that's fun. All right, that's great. And so that part's pretty much done. But let's do a little bit of diagnostics. We're going to eventually want to calculate the angle between particles after they've collided. This one is not that interested because they were perfectly aligned with each other. So with that perfect alignment, they just stayed aligned with each other. But what we can do is calculate the angle between them nonetheless, and we can use this later when we have, or actually we can use it in a few seconds if we want if we change the offset of one relative to the other. Okay, so what I'm doing is we're calculating the V1. We actually kind of already did this. And okay, like with vec norm, but this is kind of another way, right? We're compiling it, and then we're going to say we have a unit vector here, okay? Yeah, because this is calculating the magnitude. Now we want to calculate the angle between the directions that these of the velocities that these particles have. Okay. Actually, I'm just going to copy and paste. So here we go. Copy, paste, like that. All right. Like that. Like that. Okay, so those are two unit vectors. One for the velocity of particle 1 and one for the velocity of particle 2. And if we want to know the angle between these two, okay, we can take the dot product and then do the arc cosine. Remember, magnitude of A, magnitude of B times cosine theta, right? That's the dot product. So if we do the dot product of these two unit vectors, the magnitude of these two unit vectors is 1. Okay, but now we take or the magnitude of each unit vector is 1. We take their dot products, and we can we don't have to, and then we can take the arc cosine, right, and we get the angle between them. Okay, so we do that, and then if we want, we can spit this out in degrees like this. Oops, by using rad to degree. Actually, you could just use, yeah, let's just leave it at that. Yeah. Okay, so now if we do this, yeah, you get the same thing. Pause for 2 seconds, simulation runs, particles collide, and they keep going. Oh, but what did I do? Something is not right here. So line 115. Is so close to being, so arc cosine of the dot of V1. Oh, I just didn't put the underscore here, did I? Okay. Fine, we'll run the whole thing again just because of that error. And, okay, you've seen that before. And then what it should spit out, right, is the angle between the two. And that's interesting. It's telling us that it has some angle of 90 degrees. Huh. Okay, well that's possible because these are unit vectors. Let's just take a look and see what is happening at that last time step. Okay, so it's saying that V1, all right, has a velocity that's pretty small, okay, but it's in the minus 0.48, okay, meters per second. Remember, the other one, originally at first, particle was screaming at 100,000 meters per second. So, so this is now going down just a little bit, and V2, I guess, is going to be running at to the right, yeah, at the 100,000 meters per second. So what you see, because the simulation is saying that we're looking at the unit vectors here, right? Of these, because the vector velocity is downward, okay, for V1, because it's a very small, but it's been calculated here, right? You could say that's numerical error. It's telling us that, yeah, the angle between the two is 90 degrees, even though we see that that's counterintuitive, right? But that's kind of what happened, because essentially that first electron stopped. So this is not so meaningful. It would become more meaningful, right? For example, if we offset let's offset the second electron by a minuscule amount, okay, 15 nanometers. And let's see what happens then. Okay, now you can see that there's a more substantial velocity on particle 1, and this says it's 72 degrees, and that kind of makes sense. How can we make it so it even makes more sense? Well, we can actually let the plot not refresh every time, leave the hold on, and so now we're going to see a bunch of circles kept on the plot, and yeah, that looks like it could be 72 degrees. It actually looks pretty close to 90 degrees. Okay, but yeah, I would say that's closer to 90 degrees. We'll see if I made a mistake. No? Okay, but that is what it is. All right, so let's go to the next step, which is to make this work with 3 electrons. Okay, so this is going to be, we'll call this colliding 2 electrons. Okay, we'll do a save as, and then I'll try to not mess this up. I always get not always, but I often have issues with renaming and then making sure I open the new file appropriately. Okay, colliding, call it 3 electrons. Okay, so I open this up, okay, and now we're going to modify the code to add a 3rd electron. So for this, first thing is, let's go ahead and say, okay, we have 3 particles, 23 particles, 3 particles. Now, it doesn't automatically know exactly what we want, right? We gotta redefine. Actually, we can use these, though. Let's do this. The initial positions and include a 3rd electron position. So we have now, initially, let's just leave it, and leave them in line. Okay, like this. So they're all in line with each other. One's minus 3 millimeters to the left, one's at the origin, and one's 2 millimeters to the right. We'll keep the velocity profiles of 1 and 2 the same, and say that the 3rd one is also at rest, like particle 2. Okay, so we have that. Okay, and then we'll keep the time step alive, or the same. We have our pairs that will keep the same. Let's update the plotting so that it gives us the speed of the 3rd. Oops, that's not what I wanted. Okay, so speed and the x position of the 3rd particle in addition to the other 2. Okay, like that. And we'll keep those things the same. This should be the same. All this code, right? It's so nice that it's easily amenable. Okay, and then the plotting, same thing here. We will go ahead and keep that like that, but make this a 3rd particle. It's reporting on. Oh, I need to do something though important here. For the scattering, I need to plot that 3rd particle. I'm talking about it, but I need to plot it like this. Its position, and I'm going to make it green. Oops, green. So go, G-O, and yeah, that should work. But I didn't plot it. I'm going to do the hold off so I can just see them initially. We're going to put this command up in the initial, so the initial thing for 2 seconds will show us its position as well. Okay, and I'll do a Control A, and then I will do a smart indent like that, so everything comes out nice. Actually, the problem does ask us to calculate the angle between the 2nd and 3rd electron. So for this, we'll go ahead and we'll calculate out the velocity, okay, of the 3rd electron. Aha, hold on, I think now I see why we had a problem before. Look, see, sometimes you go a little bit further and you figure out, oh, it was doing V1. Alright, so my intuition was not completely off. I want to go back and fix that in this one. Okay, it's because it's V1 here. I bet you now if we run this simulation, the angle is going to be closer to 90 degrees. Let's see. Okay, so at least, well, it looked like it. Oh! Also, now I notice that it's not updating the time. Okay, we'll fix that in a second, too. Okay, look! Ta-da! Angle 1, 2, now it's 90 degrees. Alright, so I let it go, but I'm glad that I had an opportunity to go through the code. Maybe many of you probably already saw that. For the updating time, you can do dt times t, or t times dt if you want, because t is an integer, dt is that time step. All right, so now I think this will be very nice code, okay, that hopefully is useful. All right, cool. All right, and then here we're doing a hold off. This should spit out appropriate unit vectors. Well, actually, it's going to calculate them. It's not going to spit out that information, and then we're going to spit out the the resulting angle from a collision, like that. All right. So we'll have the angles between particles 1 and particles 2, and also we have there. All right. So we run it. Where's the error? Okay, go. Doesn't like that. Okay, cannot exceed 2. Oh, right, because, of course. Wait, cannot exceed 2. We have our x's. What is... It has... It's an excess of 3. Yeah, it's... Hold on, so maybe I'm not understanding this error. Line 36. The ys? Maybe I didn't update ys appropriately. Let's see. Ah, that's why. Ys is missing a... It's missing a 0. Okay, so that's that. Let's see now. Run. Okay. The particles are coming. Oh, I didn't update the time. You can see. Okay, and then boom. So it's like pool. These are perfectly aligned with each other. And they can hit each other, and they send them off. Let's update that time in the title. So right now it's just plotting 0 over and over again. But again, we can do t times dt. Okay. And so this one should work just wonderfully. Okay. And it's telling us the time up there, and it's telling us all these speeds and x positions. Okay, and that's going off, and then it should tell us that, whoops, unrecognized line 3. Okay, so V3, where is this line 125? Oh, because I guess I was getting a little bit excited. Instead of running the whole simulation again, though, I'm just going to do this. Copy that right into here, and then have it tell us the answer. Right, so the angle for 2, 3 is 0, and the angle apparently between 1 and 2 is 180. Again, if we look carefully, right, at what's going on after that interaction, okay, V1 is actually going in the minus direction, x, and V2 is going in the positive, so it's saying that, yeah, you know, these are small numbers at the end because they hit each other, and then they hit that third electron. So, you know, going from 100,000 meters per second to just a few meters per second, all right, but that's the relative direction of these velocities. And then for the problem, let's say that we want to give this some offset, that third particle, okay? And so we run the simulation, and what do we expect? We offset it, so it's the green particle is just slightly above, so we expect it to now shoot off kind of toward a positive y direction, okay? And now we say that, okay, these are at 90 degrees about, and again, this will be, I promise, the last time I run it. We do a hold on, and voila, what we should see is a bunch of, oh, it's because, nope, it's not the last time. I'm sorry, that can be a hold off. I had to go down to the last one. Okay, now I claim that this will be the last time we run the simulation for the tutorial. Okay, and we should have a bunch of circles that it's keeping there. Let me see the red one. Let me see the green one. Right? Does that angle look like 90 degrees? Looks pretty close. It's 90 degrees. All right? And it will spit that out again right here. And in this case, though, now these are moving. It was 180 degrees, I guess, but well, actually, yeah, because now the red one is like that, so that's reasonable. That also looks like it could be possibly 120 degrees between this blue and this red path right there. Okay. If you have any questions, let me know. Thank you very much for watching this video.